Hello and welcome to Advancing Vision Systems with Computar SWIR Imaging Technology. I am your host, Jonathan Hackney with Computar. First, I'm going to identify some components of SWIR imaging. The typical machine vision system will consist of the following components. You'll have your cameras, your lighting, filters, lenses, imaging processing software, and computers and processors. Some key points that we will highlight today will be how SWIR imaging can overcome visible light limitations. We'll talk about some specialized SWIR lens designs. We'll look at some unique optical coatings, and we will talk about applications, specific variants. We'll touch on all of Sony's visible plus SWIR sensors, so the IMX 990, 991, 992, and 993. And we'll show how our AR coating technology maximizes lens performance. We're going to touch on chromatic aberration correction, and we're also going to highlight Computar's SWIR series. First, let's highlight the different types of SWIR imaging. On the left, you're going to see examples of visible versus SWIR images, and it will show how the SWIR camera is designed to capture those images in that light spectrum. Hyperspectral imaging is where camera captures images of multiple wavelengths within the SWIR range. SWIR line scan imaging is where objects are scanned line by line to capture SWIR images. And then you have your SWIR thermal imaging. This is where you're combining SWIR imaging with thermal imaging to give you enhanced detection abilities. And the last point, there's SWIR reflective imaging. And that's where you're analyzing the reflectance of SWIR light for various applications, such as material identification. Now we're going to talk about how SWIR lenses work. SWIR lenses use specialized materials and coatings to effectively transmit that SWIR wavelength, the 900 nanometer to 1700 nanometer. The optical design of SWIR lenses focuses on reducing chromatic aberration and other distortions in infrared wavelengths for clear imaging. The light in the image is then focused onto an InGaAs detectors on the image sensor in the camera. The resulting image can be advantageous for seeing through opaque materials and can be used in multiple applications, including surveillance, industrial inspection, semiconductor inspection, and agricultural monitoring. So now let me introduce our SWIR Hyper APO product line. In this SWIR lens series, we'll combine the benefits of SWIR with visible. This series was specifically designed for the latest high-resolution visible plus SWIR sensors. So you're compatible with the IMX 990, 991, 992, and 993. Now with this series, you can cover 400 nanometers to the 1700 nanometers of the spectrum. Some key features for the SWIR Hyper APO series are a higher resolution lens specifically designed for Sony's IMX 990, 991, 992, and 993. As we look at the MTF graph here, we can see that the slope between a single wavelength at 1550 nanometers and the SWIR band at 900 to 1900 nanometers and the visible plus SWIR at 400 plus 1700 nanometers, they're almost identical. The lens's AR or anti-reflective coating technology provided superior imaging quality while correcting any chromatic aberrations within the spectrum. As we look at the transmittance data, we can see the effectiveness of the anti-reflective coating within that visible to SWIR spectrum. The transmittance remains relatively unchanged when imaging between that 400 and 1700 nanometers. Here we show how the internal reflection comparison between other SWIR lenses on the market compared to our VisSWIR Hyper APO series. As you can see, our lenses are designed to suppress internal reflection and adversely affect image quality by applying a special treatment to the mechanical parts that absorbs the SWIR light. And with respect to chromatic aberration, this graph shows the comparison of our Hyper APO series, which represents that blue line, and a normal visible light lens representing the red line. As you can see, there's zero focus shift for the Hyper APO lens, whereas the visible light lens shows a 210 micron of negative focus shift towards that bottom half, the 634 nanometers, and a positive 130 micron at the top end of the 1550 nanometers. The axial chromatic aberration is completely corrected in the 400 to 1700 nanometer range with the Hyper APO series. Now, because of this spectral imaging, it's now possible to simply by synchronizing the light source switch and the camera imaging as the focus does not change, even when the wavelength is changed. Now, another important feature is the lateral chromatic aberration in a lens. With large lateral chromatic aberration, the size of the image changes for each wavelength. The left side shows a typical lens for visible light. In this case, the image size is at 500 nanometers, the green line, and 1700 nanometers, the pink, differ by about 100 micron at the periphery of the image. For a pixel size of 5 micron, this difference translates into a size variant of about 20 pixels. On the other hand, as you can see, a Hyper APO is corrected so much that is almost imperceptible on this scale. As you can see, even at the point where the magnification chromatic aberration is greatest, it is only about 3 micron. If the pixel size is 5 micron, it would be difficult to see the difference in the captured image. You can see that even the 3.45 micron cell sizes used in the IMX 992 and 993 ensure sufficient performance. Furthermore, lateral chromatic aberration often changes depending on the operating distance. For example, lenses optimized for close distances will become larger at infinity, and conversely, a lens optimized for infinity will become worse at close distances as a countermeasure to this Hyper APO series uses the special focus adjustment structure called a triple helix floating structure to prevent the magnification of chromatic aberration from worsening due to distance fluctuation. This allows the lens to control chromatic aberration from infinity to close range, making it suitable for a wide range of applications. It has been highly praised for its use in food and semiconductor inspections at close range and industrial drones at long range. So now let's introduce some of the advantages of correcting that axial chromatic aberration and magnification chromatic aberration over a wide band from 1400 nanometers to 1700 nanometers. The images above are of black beans, raisins, and chocolate. from the left photographed with the color camera. Since all of the subjects are dark in nature, you can see the differences between them if you look closely, but the images are very difficult to distinguish. Now here, now here is an image at 465 nanometers. At 465 nanometers, we're only really using blue visible light. So there's not much difference from when it is taken in color. But on the other hand, when photographed at 1550 nanometers, the black beans have a strong reflection and the three become clear. The chocolate also has a slight reflection in the raisins, have no significance difference from the image taken at visible light. This is probably due to the amount of moisture contained in the subject. Now that we have both images, the one at 465 nanometers and the one at 1550 nanometers, we can do things like study the differences between the black beans, the raisins, and the chocolate much easier. But by subtracting the brightness of the 465 nanometer image from the brightness of the 1550 nanometer, now makes it possible to visualize the difference between the two, resulting in an image with higher contrast than the 1550 nanometer image. It is also possible to remove the reflective parts of the packaging materials, although this requires difficult requirements, such as lighting methods. By applying this type of image method, we believe it's possible to provide images that are easier for machines to interpret, such as when you want to check for foreign matter contamination, or when you want to use AI to distinguish between foreign objects. Using this lens, multispectral imaging is actually possible. In this example, the pulse trigger function is used to switch the LED wavelength at high speeds and synchronize the camera shutter with the LED lighting. It is possible to acquire multi-wavelength images. Furthermore, because it is a monocular camera, there is no field of view shift due to wavelength. Therefore, it is possible to handle division and addition processes such as those mentioned in the previous slide. So here's another example of that multispectral imaging using the Hyper APO series. This method can be used for a variety of things. So for the example, in this case, the sugar, flour, salt. So there's not much change at that 634 nanometers, but at 1550 nanometers, sugar is dark, followed by flour, and then salt, which becomes a little lighter. Now here's that example again, subtracting the brightness of 1550 nanometers image and the 634 nanometer image, and the result is the bottom. In this case, the glass cups containing coffee, Coke, black vinegar, and soy sauce. What you can't see in this color image is that there's screws inside the glass cups. If you switch this to the 1550 nanometers, all the liquid turns even darker. So not much different from the visible light image. But on the other hand, if we now go to, say, 1070 nanometers, the liquid is now somewhat transparent, making the screws visible within the image. Now, if we play with the images a little bit and we subtract the brightness of the 1550 nanometer from the brightness of the 1070, it now makes our vision inspection much easier. The image you can see was only from comparing, contrasting to different wavelengths, but in some cases, if we combine 3 or 4 wavelengths, it's now possible to visualize the invisible, even can make certain objects easier to see. On this slide, I wanted to introduce a popular spectroscopic camera. Some of you might have been seen something like this before, as Sony introduced the concept on their semiconductor solutions website. As seen in the image, we removed the sealing glass from the IMX 990, and we added a 4-band pass filter with different characteristics. We cut it out and glued them together and then attached to the surface. In this case, we now have a multi-wavelength spectral filter with wavelengths of 1200 nanometers, 1300 nanometers, 1450, and 16. This only allows specific wavelengths to be imaged on each area of the sensor. Now, the IMX 990 is an area sensor, so by attaching the filter that I just mentioned, you'll obtain an image like this, the one shown on the right. By determining which line to use for each of these bands and combining them with a one-way moving device like a conveyor belt, you've now just created a multispectral imaging line scan camera. So now, using our line scan camera, if we look at the image on the top left, you'll see a walnut and its skin photographed with the color camera. The color of the walnut and the skin are very close, so it seems very difficult to distinguish them with a color camera. But if you photograph this, so with each of the bands mentioned, the image of teams uh, the image of teams shown below, since the absorption spectrum of each subject is different, by extracting these characteristics and processing the image, we now can distinguish and sort a wide range of products that were nearly impossible to sort before. Similarly, the image on the right is almost indistinguishable. Look at the colored image, and we'll see like 4 separate bands, and subtract their brightness. We can easily process and sort that image. By using the multi-band pass filter, it's possible to create a spectral imaging device for inline inspection using one camera, one lens, something that was previously very difficult to achieve. So as for this multi-band filter, we now have samples. So please contact us if you want to see details. Also, the spectroscopic camera incorporating filters was provided by Aval Data. So let us know, and we can get you more information on them as well. This is the GUI screen from this from the camera and the image that was captured by them. Overall, Aval Data Viewer is easy to use, as it intuitively displays the difference between each band on the GUI. Having this ability to display different images immediately is extremely convenient. In particular, it's designed specifically for spectroscopic imaging, so very user-friendly. This is footage. Okay, so this is footage using a colored camera and the SWIR camera. The image on the left was taken with a color camera, and the image on the right was taken with a SWIR camera. This is an image of Yokohama Minato Mira, taken from the Mihama and Chiba Prefecture. Mihama is about 30 kilometers away from the landmark tower. You can see the SWIR captured clear images over the long distance. And this video is of Kawasaka Ojishima, taken from Omiha. Here too, you can see that the SWIR can capture clear images from very far away. The main reason why SWIR allows us to see further is the Rayleigh coefficient. So the Rayleigh scattering. Rayleigh scattering is a phenomenon in which light is scattered by tiny particles in the air that are smaller than the wavelength of the image, and is inversely proportional to the 4th power of the wavelength, as shown in the following formula. Therefore, the longer the wavelength, the less susceptible to this effect. So it could be said that long wavelengths are suitable for photographing distant objects, as much SWIR has many uses beyond machine vision. So going back to the three main features of the VisSWIR Hyper APO series, the first being the high resolution lens, which is compatible with the latest imaging sensors from visible light to SWIR. This lens is specifically designed to utilize the performance of the 5 micron and the 3.45 micron InGaAs sensors developed by Sony. So the second main feature is the AR coating or anti-reflective technology that maximizes the performance of the VisSWIR lenses. And the third and most significant feature is the very wide wavelength range from that 400 to 1700 nanometer with very little axial chromatic aberrations or magnification chromatic aberrations. The Hyper APO series has specifically been recognized as an optical system that can be used for all types of industrial applications for broadband spectral imaging. So on this slide, this is our SWIR reflex telephoto zoom lens. It's designed for security use. As those familiar with telescopes, we know this is a lens with a structure that combines both reflection and refraction, known as a catadioptric method. From the perspective of optical design, it's very difficult to correct chromatic aberration in lenses with long focal lengths, such as 500 nanometers or even 1,000 nanometers, in that broad band of 400 to 1,700 nanometers. So chromatic aberration occurs due to property of materials such as glass. The shorter the wavelength, the longer the bending. But this phenomenon does not occur on reflective surfaces. This lens was created by taking advantage of this property and skillfully combining reflection and refraction. And that's all I had for today. So if you have any questions, feel free to send me an email, give me a call. Thank you.